on to some story type problems. So it's 7.5, indirect measurement. We're going to do some indirect measurement examples, some scale drawings, and at the end we'll talk about comparing perimeters and areas. So some notes you need to write: indirect measurement. What does that mean when I say we're going to find indirect measurements? Well, an indirect measurement is done on something that you can't measure directly. So it's using a method with formulas or similar figures or proportions in order to measure an object. Like, what would be something that we can't easily measure with like a ruler or a tape measure? What about a cat or a capital? What about the capital?
Too tall.
Like how tall it is? Okay. The height of certain buildings would be difficult to measure directly. The distance to the moon?
No,
The size of the
circumference.
sun? Okay. I would agree that would be difficult to measure because we're not very close to it. Distance across the Grand Canyon or a river or a lake, those types of things you can't directly measure. So we're going to look at some methods that you can figure out the measurement by an indirect method.
When they like measure like things that big, don't they put approximately that size?
Probably. So we're going to try and be, some of you were maybe thinking that I'm picky when I say that 8.32 is different than 8.33. Well, if you're doing something by measurements and calculate indirectly, you're going to be off, by a number of feet, or could be miles if we're going to the moon or something. So you really have to be very precise. All right, the first example, we're going to draw some example about the width of a river. So on your notes, I know this is a very basic kind of picture, but I'm trying to picture a river here, and we're going to try and find how wide the river is. So we're going to try and figure out W. So you can make yourself a river, the two banks of the river. I'm going to show you methods related to our chapter, and so there's going to be a lot of similar figures, similar triangles going on in our diagrams. Now when we measure distance, we're measuring perpendicular, so that's why I have the perpendicular marked over there. Okay, now as far as the river, it would be hard to measure directly across it. It would be hard to measure this hypotenuse, but couldn't we measure this side of my triangle picture? Because that would be on the bank. Okay, so let's say that's 20 feet, 25 feet. All right, and then I've got another triangle on this bank that is completely measurable. I can measure it completely. Okay, and a triangle, a right triangle, let's say this is 3 foot, 4 foot, 5 foot. All right, and based on those, I'm going to change this measurement to 24. Instead of 25. Okay, now this is completely based on similar triangles, and looking at the diagram, you see the right angle in both triangles? Okay, so there's a right angle here, right angle here. Also, because of how we've set up the triangles, vertical angles are congruent. So our two triangles are similar because of angle, similarity. There is no side measurement that's making up those angles. There was no angle side. It was just angle. Okay, so we can do ratios like we've been doing this whole chapter. What sides would be comparable in these similar triangles? 24 feet and 4. Is he comparing the right things?
Yeah.
Okay, 4 feet and 24 feet. That ratio would be the same as comparing W over 3. And since these are all feet, W is going to end up as feet, and we're just cross multiplying. So 3 times 24.
72.
Okay, and then we're going to divide by the 4. And so the width of the river is 18. What kind of units?
Feet.
Feet. So it was 18 feet across. So notice how that's just based on similar triangles. using things that we can measure on the bank, and then we can figure out the width across the river. Question on that simple? Okay, let's go to another type. Step down to Vincent. Okay, mirrors can be used, probably not to find the width of the river, but in this case, the way I've got it set up, I would be measuring the height of something. So what's something we'd have difficulty measuring the height of?
Washington.
A tree, okay. So let's make a green tree here. Skinny tree, you can make your tree however you want. So there's a tree, and we're gonna measure the height of it based on a mirror. Now, in the mirror situations, the mirror is placed on the ground, and a person would need to be looking into the mirror. And this person would back up or come forward so that when they look down into the mirror, the reflection is lined up with, in this case, the top of the tree. Anyone in physical science? Okay, have you talked about angle of incidence?
Yes.
And angle of reflection?
Yeah.
Okay, that's related to what we're doing right here. Now, if I remember right, they mark those related to a perpendicular. So this is the angle of incidence, and this is the angle of reflection. I think. But in my triangles, those angles are not in my triangles, but they're both complementary, because they total 90, complementary to the angles in my triangle. So can you reason through that those two green angles are the same? So a physics type of thing is involved here. So again, we have angle-angle similarity going on. We can find the height of the tree because we can measure the distance from the mirror to the tree, let's say 30 feet. And the person is 6 feet from the mirror. And I don't really want the height of the person, do I?
Yeah, you do.
Where's the top of the triangle?
You would need it.
Wouldn't it be the eyes?
Yes.
No, it'd be that tip of that angle.
Is my triangle formed from the tip of my head or my eyesight?
Your eyesight.
So technically you need the distance up to the eyes. Okay. So that would be,
Like
I'll
6
say
now.
just 5 feet.
5.
If I'm 5'4", maybe it's about 5 feet. So based on those measurements, we can figure out how tall the tree
Big
is.
forehead.
I don't know. Making some easy numbers for you. Okay, so the 5 feet could be compared in a ratio to what from the other triangle?
H.
The H. And in the same way,
6 to 30.
6 feet compared to 30. And we've got everything in feet, so our height will be in feet when we cross multiply. So 5 times 30. H. And then divide by 6. What's the height of the tree?
25 feet.
25. Okay, so it was 25 feet tall. Question?
Cool.
Okay, again, just similar triangles.
We should
Now
try
what's going
that,
on?
like for real. Like show measure a tree using a mirror.
Sometimes we take the time. Okay, shadow examples. I don't remember if our class had a shadow one.
We did.
That was on the state review,
That
wasn't
was
it?
with the
Yeah,
light.
state capital.
Yeah, okay. So that's why you mentioned capital, okay. All right, so let's set up one in your notes for the shadow examples. What all was given in that shadow example? Well,
The length of the shadow.
the length, okay, so there was like a person,
Yeah.
is that what it was?
There's a
Okay.
person and
So there's a
Their
person,
shadow
the length of their shadow
It was 5.
is 5 feet, okay?
And they're 4.
How tall is that person?
4 feet.
So they're a shorter person, 4 feet tall?
It's a Levi.
What?
Okay.
I'm not for.
Don't have to be an adult, maybe it's a child,
Yeah, it's a child.
okay? And then we can measure, let's say we're trying to do the height of the tree again, we've gotta have something outside that casts a shadow. I don't know. Okay, so the shadow of the tree, let's go 40 feet. already wrote 40. The height of the tree is what we're after. Now let's verify that our triangles are similar. Angles, when you measure heights, you're going to go at a right angle all the time. What other angle would be the same and why? I'll think about shadows. So what's forming them right now?
It would be
The sun.
door that
Why?
when you look down,
When you look down,
it would be looking down.
if you're looking down, you would be looking more at this angle, probably, instead. You really can talk about either one. I don't know which one makes more sense to you. Where would the sun be in our picture? Okay, it'd be up here. And then the angle that the sun forms here and the angle that the sun forms here would be the same as long as you measure those at virtually the same time in the same location. So you can't measure, have somebody measure the shadow in Seward and then someone in Columbus measure the tree's shadow, because you're not close enough there, the angle will be a little bit different. So virtually the same place, the same time. Sometimes these stories will position the person or thing right beside the tree so that you're looking more at two triangles that are within one another. Maybe they have the person walk until their shadow matches up with the tip of the tree's shadow. There's different ways that they can describe this. Yes, Zach?
Since the sun is on the east to west, or we're moving around the sun, or we're turning east to west.
Okay.
If somebody like walked along latitude, like to another city directly on latitude, or longitude, whatever it would be,
Would the angle be the same?
yeah.
I would think it would be.
There probably would be some way you could come up with the same one, yeah.
Like, since we're rotating, if you did it that time and then you went to another place, that could be at the same time.
That would have to be pretty
Well timed.
mathematical, to make sure that you're on the same latitude and all that. Okay, so typically they're gonna be saying a nearby thing is measured. All right, so did I set it up right, guys? 4 feet would be compared to the height of the tree.
Yeah.
And 5 feet compared to 40 feet, the shadows compared. Okay, cross multiplying, 160 equals 5H. What's 160 divided by 5? 32. 32. So the height of the tree was, in this case, 32 feet. Okay. All right, so we're really just setting up, draw your pictures to mark your angles and your segments in there so that you know what to compare. Question before I leave that one? Okay, so what's going to make it a little bit more difficult? Oops, I went past that. The measurements. I was making them all like 5 feet, 6 feet. That's not always realistic. So here's an example where the person is 5'9", the shadow is 7'8", the shadow is 38'4". How are we going to figure out how tall the telephone pole is? And would you give the answer in inches, decimals, centimeters, what? Morgan? I would suggest that. Yeah. Okay. How do we get these into inches?
You take 7 feet and 8 over 12, and you take the 7 times 12 and add that plus 8, and that's when you get it.
That's what we did at the bell ringer today, right? Okay, so what's 7 times 12 plus 8 more?
7 plus 12 plus
Or 7 times 12, I'm sorry, did I say it wrong?
84.
Okay, and then you added 8 more? 92. So that's a total of 92 inches. 5 feet plus 9 more. So that's a total of 69 inches for that person. The shadow, 38 times 12.
38. I got it.
Plus 4. 460 inches. Okay, so we can set up our ratios. What would be the comparison? 69 compared to
H.
H. is the same as,
92 compared to 460.
okay, cross multiply for me. These are all inches, so we're gonna get inches for our answer. Cross multiply and divide so I know what the number is. How many inches is the height? 345 inches? Now, we probably wouldn't talk about a telephone pole being 345 inches tall. We'd probably say it's so many feet, so
28
many
feet,
inches.
0.75.
Okay, so how are you getting that back into feet and
Divide
inches?
by 12.
Okay, so take 345 and divide by 12. You said it was 20,
28.75. I don't know what 0.75 is.
yeah, so 28.75, what's our units?
Do 12 times 20.
Is that still inches? Isn't that feet?
Yeah.
When we divide it by 12? Okay, now, I don't want the answer that way. I want to know how many feet, how many inches. Well, obviously, it's 28 feet, okay? So 28 feet, now there's two ways, you guys can put your hands on this. There's a couple ways that you can find the other inches. If you're comfortable knowing that 28 times 12 would tell you how many total inches this is, let's go that way. 28 times 12 is how much?
336.
336? So when we subtract that from the 345, wasn't that 9? So we have 9 extra inches.
You could also times that 7.75 by 12 and you get 9.
You can. Take 0.75, the decimal part only, times 12, and that would also give you the 9. So since you knew how to do that to get these inches, I thought maybe in the end that would make sense also. So there will be some problems you have to convert. I think there's a problem that has like a decimal part of an inch. Yeah, so those will be kind of weird. Usually we go with fractions when we talk inches.
Wait, so is that our lesson?
That was the
Have we gotten to
examples.
the theorem yet?
No.
Oh,
Gotcha.
okay.
Okay, scale drawing was another type of example we said we talk about. Scale drawings use a scale to either enlarge or reduce, kind of like the dilations that we looked at on the graph paper. So a scale drawing represents an object as smaller than or larger than its actual size, just like we talked about dilations. Could be a reduction or an enlargement. Scale drawings, we usually talk about the scale or the scale factor. That's just the ratio comparing the length in the drawing to the corresponding actual length. So something you need to make sure you have with scale drawings is that the scale always compares the drawing as the numerator and the actual or real measurement on the bottom. So when, in my example up here, it says 1 centimeter represents 1,500 meters. 1 centimeter would be the measurement on the map or the drawing. The 1,500 meters would be the real life measurement the map is showing. So on the ground, that type of thing. So if you keep in mind that a scale is always the drawing measurement compared to the real measurement, that's a key to doing scale figures. Okay, so let's do it a little bit with scale. I am probably cutting out an example or two just to make sure that we give ourselves enough time. So let's talk about a map here. Okay, it's a Wisconsin map. Kristen measured a distance of 11 1/8 inch. So on the map, it's 11 1/8 inch from Madison to Wausau. The scale of the map is 1 inch, represents 13 miles. What's the actual distance between Madison and Wausau to the nearest mile? Set up your ratios that have to be equal. What's one ratio? One ratio is always the scale. So what's the scale? Well, better put the units. There will be some scales that don't have units, so that would mean you would be comparing inches to inches or feet to feet. But this one specifies, so it has to be inches compared to miles. Okay. So where's the 11 and 1/8 inch go? On the top. 11 and 1/8 inch is how many miles? Do you have to make them both into inches or both into miles? No, as long as your two ratios have the same things that they're comparing, inches to miles. So cross multiply. 1x is equal to 13 times 11 and 1/8. It says to the nearest mile. So how many miles do we get? Times 11 and 1/8. These are your little calculators. You got to think. How do you do that on a little calculator that doesn't have a fraction key? You put that into decimal.
260 miles.
Is he right?
I got 123.
Got 123.
289 and 1/4.
You guys are giving me all kinds of.
What is wrong with
He has the fraction button.
How do you
I got
get
a
1/8
fraction
in a
button.
decimal? How do you turn a fraction into a decimal? It's just 1 divided by 8.
I'll do what you want.
So you could do 1 divided by 8
289
plus 11. That would give you 11 and an 8, and then multiply by 13. Okay, let me go
I
to my
put it
next
in
one.
fraction form. I put it into an improper fraction. Is that the word?
144.65.
What is this?
Okay, so it rounds to 145,
What is this?
sounds like.
I got 164.
I don't know how you did it, you
289.
must have done something wrong. There's probably a way that you can have it convert your fraction into a decimal.
Oh, and the wrong
We
crap.
just need to investigate it. Okay, so the setup made sense, the solving didn't. Okay, let's just take a look at this one. Now notice this one has two measurements. The memorial, we're doing the floor of it, 75 feet long and 60 feet wide. There are two steps you have to do. You have to convert each one separately. So what's the scale? 1 inch to 20 feet. So you'll use that each time. Okay, 75 and 60, I'm gonna try to remember those. So 1 inch, 20 feet, we're gonna convert 75 feet to see how many inches it is when you draw it. You'll have to get your decimals into fractions. And then my second conversion is the same scale, 1 inch, 20 feet, but now I have 60 feet that I needed to convert. Why do I need both? To draw a example or a picture of a floor, you typically are making a rectangle, so you needed to know how long and how wide to make it.
Well, will we actually have to draw stuff?
Just simple things like a rectangle probably, nothing real fancy. You're mostly figuring out the correct measurements. All right, so the theorem, this is the theorem that was on your notes. Okay? This theorem is about the perimeters and areas of similar figures. So let's make an example to go along with this. Okay, let's do a simple triangle that we know is a right triangle, 3, 4, 5. And then let's double it. So if I double it, how big is it? 6, 8, and 10. So what did I make my similarity ratio? Similarity ratio comparing the sides, we made it 3 to 6, or 4 to 8, or 5 to 10. All of those reduced to be 1 to 2. So I'm going to say the similarity ratio is 1 to 2. It says the ratio of perimeters will be that same thing. So it says when we compare the perimeters and reduce it, it's still going to be, in this case, 1 to 2. What's the perimeter of this first one? Perimeter?
12.
You added, it's 12. Perimeter of this one?
24.
4. Okay, so if I compare perimeters, 12 to 24, what's that reduced to be?
1 to 2.
So notice it was the same ratio. If we double every side, the total of these and the total of these, it'll be doubled also. Area. How do you do area of a triangle?
1/2 times base time height.
Okay, so 1/2 of 3 times 4. 3 times 4 is
6 or
12,
12, so it's 6.
half of that's 6. Area of this one, 6 times 8,
48,
half of that,
24.
24. Did my area double?
No.
It was 6 to 24. So that's 1 to 4. Now, if I took enough time to do some more examples, which I'm not going to because we need to quiz, notice what they said that ratio of the areas would be. It's the square of the sides. So it's 1 squared compared to 2 squared, which is 1/4. The area ratio is always the square of what you do to the sides. And if you'll think about the kind of units you use on areas, we label those as like square inches or square feet. That might help you make a connection between the square ratio.
When you have like the 6 over 24, where do you get the 6? Like why
6
is
was the area of this small one. Area of I just put the actual areas there
Oh, okay.
to show.
Now I get it.
Now, we'll come back to this section in another chapter, but what I'm going to have you do today is simply this type of question. If the similarity ratio of the similar polygons is 4 to 9, what's the similarity ratio comparing? Similarity ratio, what do we define that to be? What are you comparing? The sides. Okay, so the sides compare in a 4 to 9 ratio. What will the ratio of the perimeters be? Is it the same or is it different? The perimeter one is the same, so the perimeter ratio is 4 to 9. The ratio when you compare areas would be the square of it,
So
16 to 81. Now this does not reduce to be 4 to 9. You don't reduce by square rooting. You have to divide by the same number. Sometimes we think that you can square root and reduce it. And for the last example, 2 pentagons are similar. The perimeter of the smaller one is 20 inches. The perimeter of the larger one is 50 inches. So what's the ratio of the perimeters? What's the ratio when I compare perimeters? 20 to 50, does that reduce? 2 to 5? Okay, that's the perimeter ratio. Now what's the similarity ratio of just the separate sides? What did you say? 2 to 5, it's the same.
Yeah.
The perimeter ratio and similarity ratio are always the same.
4 to
The ratio of the
25.
areas
4 to 25.
is the square of it, 4 to 25.
So how do you get the similarity ratio from like the 20 and 50?
From the 20 and the 50, I would know that the ratio of the perimeters is the same as the ratio of
Just
the...
because of the perimeter.
If I gave you the bottom one, if I gave you the ratio of the areas, you'd have to square root it to get these 2 ratios. So you'll go from one ratio to the other. That part will be all we're doing in that section today. All right, so the area ratio is different. It's the square